Here we are going to study the process resolution and the methods which are used for resolution. Resolution is the process of separation of enantiomers from a racemic mixture. It is the process of separation of pure enantiomers from a racemic mixture. That is, if we have a mixture of tartaric acid, that is, if we have a mixture of plus and minus tartaric acid, the process of separation of pure plus tartaric acid or pure minus tartaric acid from this mixture is known as resolution. And resolution can be done by using different methods. The most common methods used for resolution are, the first one is mechanical resolution. Mechanical. And the second one is biochemical processes. Biochemical. Then we can use some chemical processes for resolution. Then differential adsorption is a method. Same way we can use differential reactivity or kinetic methods. So the other methods are differential reactivity or kinetic methods. And the first scientist who worked for resolution process of racemic mixture is Pasteur. The first method is mechanical separation. Mechanical separation is the simplest method for the resolution process. It is the simplest method. Actually, this process is only applicable for the enantiomers which are exist in well-defined crystal form. So, it is applicable only for well-defined crystalline forms of enantiomers. For example, resolution process of racemic mixture of tartaric acid can be done by mechanical means. Plus and minus tartaric acids exist in well-defined crystal forms. So, we can easily separate the plus and minus form by hand picking. If we have a magnifying lens and a forceps, then we can easily separate the plus and minus tartaric acid from this racemic mixture. This is the simplest process. The second one is biochemical methods. Biochemical separation methods are done by using microorganisms. That is, in nature, there are some microorganisms which consume some particular enantiomers. So we can use these microorganisms to separate a particular enantiomer from a racemic mixture. For example, racemic mixture of tartaric acid If we allow to grow penicillium glaucum in racemic mixture of tartaric acid, this microorganism, that is penicillium glaucum, consume plus tartaric acid from this racemic mixture. So consume plus tartaric acid. So the only enantiomer left behind this racemic mixture is minus tartaric acid. So by using penicillium glaucum, we can separate minus tartaric acid from the mixture of plus minus tartaric acid. So enantiomer which will not consumed by the microorganism can be separated out from the racemic mixture with the help of these microorganisms. But we cannot always use this method for the separation method, because the first demerit of this method is this is a slow process. That is time required to grow this microorganism within this racemic mixture, and we have to give time to consume this particular enantiomer by this microbe. So this is a time consuming process. And the next one is, we cannot always separate the racemic mixtures by using microbes, because there are some enantiomers which are poisonous in nature. So these microbes cannot consume these poisonous enantiomers. So it is not applicable to poisonous enantiomers. Then third demerit is, we can only separate very little bit amount of enantiomers from racemic mixture. So the amount of isomer leaving behind is very small. Amount of enantiomer leaving behind is very small. That is, 1/2 of the compound initially taken is consumed by the microbe. So we'll get only half amount of the substance we are taking for the resolution process. So half of the fourth demerit is, half of the compound is consumed. During the process. So these are the disadvantages of this method. The third one is chemical method. The process involved in chemical method is the conversion of the racemic mixture that is mixture of enantiomers into diastereoisomer. What is the significance of this conversion? We know enantiomers possess almost same physical properties, so it is difficult to separate. On the other hand, diastereoisomers differ in their physical properties in a large extent. So it is easy to separate the diastereoisomers by using simple physical methods. So the separation of racemic mixture is easier when it converts to its diastereomer. After converting this into diastereomer, we can easily separate it out the enantiomer from the pure diastereoisomer by simple process like hydrolysis. So how can we convert a racemic mixture or an enantiomer into diastereoisomer? There are some chemical reagent or there are some optically active reagent which can convert enantiomer into diastereomer. For example, plus minus lactic acid can convert into its diastereoisomer with the help of an optically active reagent called minus brucine. So if we treat racemic mixture of lactic acid with minus brucine, this lactic acid will convert to its diastereoisomer. That is, this is plus lactic acid and this is minus lactic acid. This is D form and this is L form. So this is a racemic mixture. So a mixture containing both D and L. When we treat this compound with L brucine, that is minus brucine, what happens is this brucine will react with these two enantiomers and form a diastereomeric mixture. That is, this form CH3COH COOH brucine and this convert to its diastereomer, that is OH COOH brucine. Here this end is D and this is L. Here these two are L. That is a mixture of diastereomer. Now we can easily separate these two by using simple physical methods. So we can separate this compound and this compound. So by obtaining this pure compound, we can convert this into the enantiomer, the pure form of enantiomer, by hydrolysis. That is, if we hydrolyze this compound, we will get CH3COH and COOH. That is pure L form plus L brucine. Same way, if we hydrolyze this compound, we will get pure D form of lactic acid and brucine. This is the process occurs in chemical resolution methods. The next method is differential adsorption. So here racemic mixture can be separated by using adsorption process. That is, we can separate the racemic mixture by using chromatographic technique. Actually, some enantiomers shows greater affinity towards some particular adsorbent. The next enantiomer will not show that much affinity towards that adsorbent. So that is the principle which we are using in differential adsorption method. That is, consider we have a racemic mixture and the plus and minus. If minus mixture, that is L enantiomer, shows greater affinity and the plus one shows lesser affinity towards an adsorbent, then we can easily separate these two isomers by using chromatographic technique. So the method involved is we have to fill a column with an optically active adsorbent or an adsorbent containing an optically active compound. So the column is filled with a optically active compound. Then we have to fill our mixture into the column. And during the chromatographic process, the enantiomer shows greater affinity, will adsorb easier with this adsorbent, and the next enantiomer dilute very easily. So we can separate the D-enantiomer from this mixture because N shows greater affinity towards the adsorbent. If plus shows greater affinity towards the adsorbent, then we'll elute minus enantiomer first. This is the process involved in differential adsorption method. This method, differential adsorption method, is normally used in mandelic acid. DL mandelic acid can be separated by using starch as an adsorbent. Then the last method is differential reactivity or kinetic methods. This method is used when one of the enantiomers shows greater affinity towards a particular reactant. For example, in DL mandelic acid, when we add L ethanol to the mixture of mandelic acid, the D-mandelic acid shows greater affinity towards L-ethanol. So D and L combine to form ester. So D-mandelic acid and L-ethanol react and form a D-ester. L-ester will also form there, but the amount will be very less. Since the affinity of D-mandelic acid toward L-ethanol is very fast, D-ester will be easily formed within this mixture and we can easily separate D-ester from the mixture. So these are all about the resolution methods.